This video will cover cross-validation as part of your modeling process. By the end of this video, you should understand how to efficiently use data for both training and test data, what the steps are in k-fold cross-validation, and what are some other cross-validation methods. As we've seen before, out-of-sample validation is a best practice in model selection. It helps to reduce overfitting, but it doesn't eliminate it. Why is that? Well, for example, what if there's something weird about your training data or your test data? What do I mean by weird? There might be something odd in your data that causes the models that are trained on it to make inaccurate predictions. How would you be able to tell if your data had something weird? Well, you could wait for more data to come in after you train models and look at the forecasts and see how well they do. But is there a way that you could check the forecasts from a model using new training and test data without waiting for new data to come in? And very broadly, to protect against overfitting, we'd always like to have additional training and test data. But the problem is, how are we going to be able to get more training and test data? Well, just like before, when we divided our data into training and test data, we could instead divide it 4 ways. We could create 2 training samples and 2 test samples, and then train 2 sets of models, 1 on each training sample, and then look at the forecasts on the test samples. This is a step in the right direction, but there's actually a way to make much more efficient use of the data that we have, and this process is called k-fold cross-validation. So how does k-fold cross-validation work? What you'll do is you'll divide your data into many, in fact, the number is k, subsets called folds. You're going to choose some of those folds to use as the training sample. You'll train your model on that sample. Then you'll use the remaining folds as your test sample, and you'll compute the value of the loss function out of sample on those remaining folds. You'll then repeat this process using different folds as the training and test samples. You'll do this several times, and then you'll take the average of the loss function computed out of sample across all of the iterations. And then you're going to choose the model as your preferred model that has the lowest average value of the loss function across all those iterations. Let's look at two-fold cross-validation graphically. Suppose you have some data. If you're performing two-fold cross-validation, you'll divide that into 2 folds. I'll call them fold 1 and fold 2. You'll use fold 1 as your training data, and you'll train your model on fold 1. You'll then use fold 2 as your test data and compute the value of the loss function on fold 2. After that, you'll use fold 2 as the training data, training your model on that fold 2 data. That will give you a second trained model that you can use to compute the out-of-sample loss on fold 1. After you've done this twice, you have 2 values of the loss function, one computed using the model trained on fold 2 and tested on fold 1, and the other computed using the model trained on fold 1 and tested on fold 2. You'll take the average of these 2 loss functions and use that as your best estimate of the loss function on model 1. You'll then repeat this process for every model that you would like to consider. You'll compare the average loss across all of those models, and your preferred model will be the one with the lowest average loss computed out of sample through all of those k-fold iterations. The example that I've given you here uses 2 folds, but why stop there? This process generalizes to any number of folds. And this is what's called k-fold cross-validation. Again, you'll divide your data into k folds. You'll choose some of the folds, usually k-1 as your training sample. Then you're going to compute loss on the remaining fold. You're going to repeat this for all possible combinations of folds, and then you're going to choose the model with the lowest average value of the loss function across all of those iterations. What's the correct number of folds? The reason we call it k-fold cross-validation is there is no correct number. More folds means that your test data is smaller. Remember that the number of observations in your test data is the number of observations divided by the number of folds. With fewer observations in the test data, it's more likely that something weird happens in it. As you add more observations, it's likely that weird things might average out. Adding additional folds means that you have more estimates of the loss function, however. And so this means a better guess of the out-of-sample loss. So while additional folds reduces the size of your test data, it also gives you additional estimates of the loss function. Each of these features would be good, which is why there's no correct number of folds. In general, people choose 5, 10, or 20 folds. Larger data sets should use more folds. Be aware though that time can be an issue. 20-fold cross-validation takes 4 times as long as 5-fold cross-validation. With complicated models, these additional cross-validation steps can take a very long time, so computation time may eventually become a consideration. The Tidyverse includes packages that assist with k-fold cross-validation. They include features for automatically dividing data, training models, and computing loss. K-fold cross-validation isn't the only cross-validation method. There are many other examples. A couple of common methods. There's leave p out cross-validation. In this method, you choose some number p You select P observations to use as test data, and then you train the model on the remaining data. You then compute the loss function on your test data. You're going to repeat this for all possible combinations of P observations. You can imagine there are many, many different ways to draw a small number of observations from a large data set, so this approach can be very, very computationally demanding. Another alternative is repeated random subsampling. In this method, you're again going to choose a test sample size of P. You'll randomly select P observations to use as test data, and then train the model on the remaining data, compute the loss function on the P observations you held out. Unlike leave P out subsampling, you don't repeat this for all possible combinations, you just repeat as many times as you would like. Repeated random subsampling is a somewhat computationally attractive method, but it requires a lot more iterations to get the same accuracy as k-fold cross-validation, which is why k-fold cross-validation is generally the preferred method of cross-validation.